All right, as promised, I'm going to do the effective resistance of this part. And we'll have to do the same thing that we did for the capacitor, which is, since the current flows this way and this way, we have to get the effective resistance for this part, the parallel part, first. And then after we get it, we can put it in here for the series part. Now you'll notice that for the series part, I have a different equation. In fact, I just add whatever the effective resistance of this is, which is our parallel, to this, and that's going to give me the effective resistance of the entire thing. The parallel part is going to have the inverse method, so that's going to be 1 over R plus 1 over R. So remember, with the capacitor plates, there was a physical way to think about that. In this, it's the same thing. If you have two of these resistors in parallel, it's like having double the area, since they're the same resistance. It's like having double the area. It's like summing their areas as long as they have the same resistivity. And then when you add another one, that's like increasing the length. So you increase the length, you increase the resistance, you increase the area, you reduce the resistance. And that's more or less what's happening with these two equations. The different physics of the resistor, which is losing energy as it goes through, and the capacitor, which is storing energy, means you end up with basically the opposite relationship between for the effective resistance as the effective capacitance as far as series and parallel is concerned. And we have all the same sort of rules that we have there, right? So first, the part that's in parallel, then the part that's in series. Next, after that, since this does have to do with power loss, we'll go ahead and do a power loss part as well. That's going to be the last part of the thing here, because we're going to use the power loss. This is not rate of charge. This is the rate of heating, and that's going to be V squared over R. And we're going to use this 9-volt battery to do that. So you want to do this parallel part. Our parallel is equal to 1 over R plus 1 over R. And these are both 1 over 100 ohms. So that's going to be 2 over 100 ohms, or 1 over 50 ohms. So if 1 over R parallel is equal to 1 over 50 ohms, then our parallel is just 50 ohms. So I've just taken that 2, right, and I've brought it down here. So we have 100 ohms over 2. That's 100 over 2 is 50. So this is all the old algebra stuff. It's the complicated algebra stuff that you really, really loved in high school. So we've got that part from the R parallel. Now that can come back up here to find our effective resistance. And that's going to be 100 ohms, this guy, plus 50 ohms, this guy. Right? And if we add those two things together, we get 150 ohms. So now this part's a little bit easier because you don't have to do the inverse. So now we've seen sort of the differences between the capacitor and the resistor as far as finding the effective capacitance and the effective resistance. Last thing I want to do is actually look at the power loss, like I said. And that rate of heat generation, the power loss, is V squared over R. I've connected this to a 9-volt battery, so that's 9 volts squared over the resistance that I just calculated, which was 150 ohms, which is 81 over 150 volts squared over ohms. 81 over 150 is 0.54, and V squared over omega, or volts, square volts over omega over ohms is, it turns out, watts. Okay, so we don't want to go through all that, but we could go all through that if you really, really wanted to. So there we end up with our happy power loss. So that's how much energy we're using as the electrons pass through. I guess the electrons are passing through the other way, these resistors. All right, so what we did, just as before, we did the same thing. We wanted to find this R parallel, right? This R parallel we want to find before we find the effective resistance in series, because we can't really do that. So we can't take this part and that part alone because they have a common resistor. So what we have to do is we have to collapse this part first before we hit the series part. So again, parallel part first, series part second. The parallel part uses some of the inverses because it's like increasing the area of the resistor, so that's reducing the resistance. And the series part is adding the resistance. It's like lengthening the resistor. How much you lengthen the resistor depends on what's actually happening. And in this case, we have what ends up being a smaller or larger area when we lengthen it out. And so that's a little bit weird. We don't have an equation for that, but we do have a way of taking two parts and putting them together. In fact, you could do this if you wanted to. You could use these formulas to find the effective resistance of something with a wider area and a smaller area, just if you want to. You don't have to do it, but it's something you could do at night. I mean, it's not something that's going to scare you or anything like that, I hope. Okay, so that was the big point of this particular thing, is first you do the parallel part, then you do the series part. All right? Great. So I'll talk to you next time. Bye now.